All right, guys, section 2.2, change in linear and exponential functions. And so what we're looking to do in this video is talk about our arithmetic and our geometric sequences and types of functions that they are very similar to. So arithmetic sequences, we've had this formula that we've been working with for a few days. And this formula is very similar to one that you learned in Algebra 1 called point-slope form. Point-slope form is often used in place of y equals mx plus b. They're both equations of linear functions, but it looks like this. If we have y minus y1, that's going to equal to m, the slope, times x minus x1. So what lines up in these two formulas, d is the same thing as m. So the common difference is just our slope. N minus k is like x minus x1. The only thing that looks different is we've got a sub n equals a sub k, where this is y minus y1. But if we just added that y1 over to the right, now it says y equals y1 plus this. All right, so again, the connection here is that arithmetic sequences are very similar to linear functions. Now, this last part's a reminder. This is something that we attempted to memorize towards the beginning of the year, that over equal length input value intervals, linear functions change at a constant rate. All right, and so that's going to be useful towards the end of this video, but linear functions change at a constant rate just means their slope stays the same. Just like with arithmetic, the common difference stays the same. All right, let's talk about geometric functions. So geometric functions are set up very similar to exponential functions. And so you would have learned in Algebra 2 that exponential functions can be written as y equals a multiplied by b to the x. All right, and so again, you can see these formulas are very similar. What's not there is the minus k. But as we do transformations, if we're subtracting a number from x, that's just gonna, or adding, it's just going to move it left or right, the graph. And so we're not going to put that as part of the formula. But if there's a plus there or a minus there, it just moves it left or right. Now, this part's new, and it says this, that over equal length input value intervals, exponential functions change proportionately or by multiplication. All right, so just like our geometric functions have that common ratio, exponential functions, we don't call it the ratio or the common ratio, but exponential functions are going to change by multiplication or, again, change proportionately. So here's the main type of question we would need to be able to answer from this lesson. So we're going to label each of these as either linear, quadratic, cubic, or exponential. So I like to look for exponential first. With exponential, our output values are going to change by multiplication or change proportionately. So the only one up here that I see where the y values are changing by multiplication is this first table. Right, from 100 to 50, we're multiplying by 1/2. Same thing as dividing by 2. Then we're multiplying by another 1/2. And then we're multiplying by another 1/2. All right, so if the y values are changing by multiplication, then this is automatically an exponential function. For the next two, so let's see. And by the way, I should double check. The x's are increasing by the same amount each time. We're going plus 3, plus 3, plus 3. Same thing here. The x's are changing by the same amount. Let's see what's happening with the y's. So if I subtract 3, and then 3, and then 3. So because the first differences are all the same, that tells us that's a linear function. Right? It's like having that common difference here. And again, this was like having that common ratio. All right, so linear and exponential. The last one, the x's are all increasing by 5. It doesn't matter what the x's are increasing by as long as they're the same each time. The y's are decreasing by 3, decreasing by 2, and decreasing by 1. So that tells us it's not linear. Then if we look at the next row, from -3 to -2, we would add 1. And then from -2 to -1, we would add another 1. So this is a quadratic function. Also, this is, I didn't ask this, but we have previously in the course been able to answer what the graph looks like. So because the second differences were positive, this graph would open up or be concave up. All right, if the second differences were negative, that would tell us that the graph is opening down or concave down. All right, so that's literally all of section 2.2. I will, again, make it extra credit if you memorize this right here. and you memorize this right here. Okay, and it does need to be word for word, right? Or mean the exact same thing if it's not verbatim from what's up here. All right, so that's it, guys. Stay flawless.